Hi everyone, I'm going to be talking about Lab 4, which is on resonance. And so last week you were looking at waves, and one thing that you notice is that on a standing string at certain frequencies, the wave sort of made a sinusoidal shape. And so that's an example of resonance where waves are essentially adding together to create this ordered structure. So the lab starts off with part one by just reintroducing the equation or like the mathematical model for a wave. And then it reminds you that the velocity is equal to the square root of the tension on the string divided by mu, where mu is the mass divided by the length of the string, or otherwise known as the linear mass density. And so all you're going to do in part one is you're going to look at the data that you collected last week and then calculate a velocity using this root t over mu, using the values that they give you here, and you're just going to see if it agrees with the values that you found last week. All right. And so in part two of the lab, you're going to be thinking some more about oscillation in general and not really thinking too much about resonance yet, which is kind of funny given that the lab's on resonance. But what they do is they just remind you in the first lab that we saw that the frequency of a spring is equal to the square root of k over m, or 1 over 2 pi times the square root of k over m, where k is the spring constant, m is the mass. And they say if we just multiply both sides by some displacement x, then we get this equation down here. Okay? And so, really quickly, what they're doing is they have 1 over 2 pi root k over m, and then they multiply it times x squared. Maybe I'll use a dot instead of a times, or not times x squared, sorry, just times x, right? And this is equal to 1 over 2 pi root kx squared over m. And then they break this x, they break it into um, uh, x times x, and then they put one of those x's under this m. So then this ends up equaling 1 over 2 pi root kx over m over x. And the reason this works is because when you divide by m over x, you multiply times x over m. And so this x ends up moving to the top. And so that's fine. So that's all they're doing there. And then they ask you to just think about different systems and then how they're similar to a spring. And that's okay. And that's not, we still haven't even gotten to like the actual lab part where you do an experiment. But the thought experiment tells you to think about resonance or like this combination of waves in 2 dimensions. And so that actually relates back to this image that they put up here. So if you put sand on a plate and then you vibrate the plate at different frequencies, if you're at resonant frequencies, you'll see different patterns form. And so these are called Chladni plates, which they mention down here. So they mentioned that they're called Chladni plates. So you can find videos of it online if you just look up Chladni plates. And then part three is where you do like the actual experiment. So they propose that the velocity of sound might be equal to the square root of p over rho, because we're just going to pretend that p, it's not really pretending, but like they're like guessing that this pressure is like similar to the k term, and then this rho is like similar to the mass term, and then this equates to, or it's like similar to root k over m. And so they're sort of proposing that this is true. We don't necessarily know that it's true yet, but the first part just asks you to like check the units and make sure that this equals meters per second. And then actually one thing really quickly was that I forgot to mention that when we multiply frequency times x, we get units of 1 over seconds times meters, which equals meters per second. So that's why we're saying it's a velocity. And then where you do the actual lab is when you look at this tube of water with like a PVC pipe in it, and you have a tuning fork. And so what you're gonna do is you're gonna calculate what height the tube should be at, or not the tube, what height the PVC pipe should be at in the tube in order to get resonance. And so one of the questions in the lab is like, what is the resonance? Like, how do you know if you have resonance? Like, you'll hear it. You'll be able to hear if you have resonance. And so you're just gonna use the tuning fork at different heights of the PVC to find when you have resonance. And what you're going to do is you're going to end up calculating the speed of you're going to calculate the velocity of the sound waves in the air from your experiment, and you can compare that to the theoretical speed, which is like approximately 343 meters per second, and you're going to see if they're similar. And they should not be similar according to this, because it says, is our resonance model valid? Hint, it isn't, meaning that the experimental velocity you get is probably not going to be similar to the theoretical velocity. And then the last part is you're going to use the speaker, and you're going to play different frequencies, and you're going to see that only frequencies that show up for odd harmonics produce the resonance in the tube. And that's fine. And then I'm not going to actually go too in depth into the thought questions at the end, because they're actually like absurdly difficult this week. So don't stress too much about them. The first one just gives you this equation for the speed of sound, and then they put this like square root of gamma in front of it, where gamma is like some constant, and then they're asking like physically what is gamma. The second part is that like one form of energy that exists in every system but is difficult to quantify is heat. And then it's just asking, when we were thinking about the spring, did we account for heat energy in the medium? So that's one thing to consider. And then 4.3 is talking about explaining the mechanism by which heat energy can affect resonance in sound waves. So like if you heat up molecules, air molecules, how does that change the sound waves that travel through them? And then the last part is like really difficult. This one is asking that, like, if you replace all the bonds in these particles with springs, you know, how might one go about calculating the resonance of the entire 3D structure if all of these bonds are springs? And that's really difficult. So don't worry about that. But that's this lab this week. So resonance is really cool. So I'm excited to do the lab with you guys, and thank you.